welcome back. In the last lectures, we have seen the importance of three-dimensional to two-dimensional idealization. We have seen the mathematical formulations related to 2D idealization, where the important 2D idealizations we have seen are plane strain, plane stress and axisymmetric condition. Out of this, the mathematical formulations related to plane strain and plane stress we have discussed. So, in today's lecture, we will see the mathematical formulation for axisymmetric condition. So, here we are dealing with linear elastic isotropic condition. In the previous lectures also we have done for the simple linear elastic models. So, here also we will see for the linear elastic formulation. Now, in this axisymmetric condition, we have already stated that this is very important with respect to soil behavior. Why? Because the triaxial samples what we discuss falls under axisymmetric formulation. So, we will now in the formulation for axisymmetric condition we will specifically focus on triaxial sample. You can see that this is the cylindrical soil sample which is acted upon by axial stress, and axial stress is normally considered as the major principal stress, and the radial stress, the all round stress or the radial stress is the minor principal stress. So, this is axial and this is radial. So, this is the situation. So, if you see that if sigma 1 is exactly acting at the center, is an axial load. So, it has to act at the central axis. If this is considered as the reference, then this is symmetrical about the application of this load. It is also symmetrical with respect to its geometry. So, it is important that these are met. Additionally, in this particular formulation or in this particular triaxial sample, we know that sigma 2 is equal to sigma 3. The radial stresses are all round stresses are same, and to maintain the geometric symmetry we also need to have epsilon 2 is equal to epsilon 3, that is for maintaining geometric symmetry. Now, we know the formulations which we have already seen before. The formulation was let us say in general epsilon x is equal to sigma x by E minus mu by E sigma y plus sigma z. So, this is the general equation. Now, we are considering in terms of principal stresses. So, we have sigma 1, epsilon 1 is the major principal strain is equal to sigma 1 by E minus 2 mu sigma 3 by E. Why? Because here sigma 2 is equal to sigma 3, hence it will become minus 2 mu sigma 3 by E. So, that is denoted as equation 1. Then we have epsilon 3 is equal to sigma 3 by E minus mu sigma 1 plus sigma 3 by E. So, there is no need of epsilon 2 because epsilon 2 is equal to epsilon 3. So, epsilon 3 is equal to sigma 3 by E minus mu sigma 1 plus sigma 3 by E, and that is denoted as equation 2. And epsilon 3 is equal to 1 minus mu sigma 3 by E minus mu sigma 1 by E. That is, if you rearrange this sigma 3 and minus mu sigma 3 by E, we get 1 minus mu sigma 3 by E minus mu sigma 1 by E. Okay. So, based on epsilon 1 and epsilon 3, one can always arrange the constitutive relationship for axisymmetric condition in matrix form. This we have done for plane stress and plane strain as well. The same constitutive formulation has been done for axisymmetric condition as epsilon as a function of stress. So, epsilon 1 epsilon 3 equal to 1 by E 1 minus 2 mu minus mu 1 minus mu sigma 1 by sigma 3. Now, one thing we have to note here is if you consider this particular matrix, this is not a symmetric matrix. You have minus 2 mu and minus mu here. So, this is something different from what we have seen earlier, where we had a symmetrical matrix. So, in this case it is not symmetric, hence the inverse may not be straightforward. I mean to say, if I get the equation for sigma 1, that will not apply for sigma 3. So, that we will have to see separately. So, this is the constitutive relationship in terms of epsilon 1 and epsilon 3. Now, we also need to know what is the inverse relationship, that is what will be sigma is equal to E into epsilon. So, we also need to know this particular inverse relationship. This we have seen in the earlier lecture also. We need to do some mathematical rearrangement and simplification, so that we get the relationship in terms of sigma. So, for that we need to do some modification for equation 1. So, 1 is multiplied by mu, which gives mu epsilon 1 is equal to mu sigma 1 by E minus 2 mu square sigma 3 by E, and that is denoted as equation 3. Why we are doing this? We are doing this to eliminate 1 by 1, and we are left with only one stress, and that will give you the required equation. So, we are just eliminating it. So, then this equation plus equation 2, equation 2 is for epsilon 3. So, that will give you mu epsilon 1 plus epsilon 3 equal to 1 minus mu sigma 3 by E minus 2 mu square sigma 3 by E. I again strongly urge all of you to please write it down step by step and make sure that it is all right. Again, if you can see with this particular operation, you can see that this is now in terms of sigma 3. So, sigma 3 by E, if we take it outside, we have 1 minus mu minus 2 mu square, and with some adjustment, that is plus mu minus mu, you will get a proper equation. So, sigma 3 by E 1 minus 2 mu minus, that is minus mu, that will give you minus 2 mu square plus mu. Further, if you again rearrange this, you will get sigma 3 by E 1 plus mu. So, this plus this 1 plus mu, if we take minus 2 mu outside, it will be 1 plus mu. So, again 1 plus mu can be taken outside, this will give sigma 3 as E divided by, so if you take 1 plus mu outside, here it will be sigma 3 1 plus mu, and you are left with 1 minus 2 mu. So, sigma 3 will be equal to, E will go on the other side, E will go here. So, that will read E upon 1 plus mu 1 minus 2 mu epsilon 1 plus epsilon 3, which is from here. So, that is the equation for sigma 3. In the earlier lectures, we have seen that once we have got it for one particular stress, you can just reproduce it for other stresses as well. There, in that particular case, you could see that the matrix was symmetrical, where epsilon in terms of sigma was symmetrical. But in this case, it is not symmetrical, hence we cannot reproduce for sigma 1, we have to again find it separately. So, we will see how. If you multiply equation 1 by 1 minus mu by 2 mu, why we are doing this? We need to find sigma 1 expression. So, multiply 1 minus mu by 2 mu, this will give 1 minus mu by 2 mu into epsilon 1 is equal to 1 minus mu by 2 mu sigma 1 by E minus 1 minus mu sigma 3 by E. So, call it as equation 4. Now, if we again do this operation 4 plus 2, we will be left with this 1 minus mu by 2 mu epsilon 1 plus epsilon 3 equal to 1 minus mu by 2 mu sigma 1 by E minus mu sigma 1 by E. So, sigma 3 got eliminated in this operation. So, this we are left with now sigma 1. Now, we need to rearrange it. If you multiply by 2 mu, we will be left with 1 minus mu epsilon 1 plus 2 mu epsilon 3 equal to, take 1 by E outside, then we are left with 1 minus mu sigma 1 minus 2 mu square sigma 1. So, sigma 1 by E can be written as 1 minus mu minus 2 mu square. So, this again can be further simplified, which will give 1 minus mu minus 2 mu square is equal to 1 plus mu into 1 minus 2 mu. Substitute it back here, we can write the expression for sigma 1, which is equal to, E will go on this side, E upon 1 plus mu into 1 minus 2 mu into 1 minus mu epsilon 1, which is written here, 1 minus mu epsilon 1 plus 2 mu epsilon 3. So, one can again rearrange the constitutive relationship for axisymmetric condition in matrix form, that is stress in terms of strain, as sigma 1 sigma 3 equal to E upon 1 plus mu 1 minus 2 mu. You will have 1 minus mu 2 mu mu 1 epsilon 1 epsilon 3. Again this is not a symmetric matrix. Now, let us see what is the application of these constitutive relationship. We will see this with a simple example, whereas the same constitutive relationship can be used to solve complex problems as well. But for understanding it better, we will see a very simple example which may not need constitutive relationship as such to solve the problem, but for us to understand how this can be applied. So, how to apply constitutive relationship for plane strain and axisymmetric condition? I am purposely avoiding plane stress because we are in advanced soil mechanics, this particular course, and specifically in geomechanics, we will have a lot of plane strain and axisymmetric cases. So, the first example is that there is a retaining wall with outward movement. Outward movement means we know that it is an active condition. Also, lateral strain and vertical strain of a soil element behind the wall are given, it is given. We need to calculate change in stresses acting on the wall. To calculate the lateral force per unit length acting on the wall. Now, we are supposed to calculate what are the changes in the stresses due to this movement. Now, due to this movement outwards, which is an active condition, the strains are given. I purposely avoided the values here because the same will be attempted in assignments. So, you just need to understand how or what is the logic by which we can use the constitutive relationship. So, retaining wall, what is the speciality of a retaining wall? We have already seen that the behavior of a retaining wall can be idealized to a 2D behavior, and that too in terms of plane strain, because the length in one direction is long as compared to the cross section and the strain in one direction. So, we are dealing in principal stresses and principal strain. So, the epsilon 2 can be considered equal to 0. So, this is a retaining wall. We are talking about a given soil element whose lateral and vertical strain is given, and this retaining wall is moving outward. So, we know since it is a plane strain problem, we know that we can apply this particular constitutive relationship. So, here I have added delta sigma 1 just to show that it is change in stress. So, delta sigma 1 delta sigma 3 is equal to E upon 1 plus mu 1 minus 2 mu, 1 minus mu 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 1 minus mu delta epsilon 1 delta epsilon 3. Here you note that this is a symmetric matrix, which is different from the asymmetric matrix that we obtained in axisymmetric case. Now, what is given? Delta epsilon 1 delta epsilon 3. Now, once we know delta sigma 1 and delta sigma 3, we can always calculate change in stresses by knowing the elastic parameters also. Okay. One more thing we need to understand here is, in this problem we are assuming everything to be linear elastic. Now, how far it is true, how far it is close to reality, that is something different, but here we are assuming the behavior to be linear elastic. So, this is an active condition, we have already discussed that. Horizontal change in stress will be delta sigma 3. In active condition, we have minor principal stress acting horizontally. So, what we are looking at is delta sigma 3. Now, once you substitute the values of delta epsilon 1, delta epsilon 3, mu and E, we can determine delta sigma 1 and delta sigma 3. Now, delta sigma 1 is in vertical, delta sigma 3 is in horizontal because it is a movement outwards. Now, once we know delta sigma 3, we need to find out what is the lateral force per unit length. So, you are just determining the force. Now, what is the force? This can be done by integrating delta sigma 3 for the entire height of the retaining wall. This will give us lateral force per unit length. Same problem with its numericals we will see in the assignment. So, another case is given an oil tank founded on soil. Vertical and lateral stresses at the middle of the soil layer is known. To determine the strain and elastic vertical settlement. So, it is specified here, it is elastic vertical settlement. So, our problem becomes linear elastic. Now, cylindrical oil tank with soil element beneath the central axis, it satisfies the axisymmetric condition. We will see how. Now, consider this to be the cylindrical oil tank. Now, we are considering a soil element which is exactly beneath the central axis of this cylindrical oil tank. If you are considering this, then it obviously satisfies the requirements of axisymmetric condition. Once we know it is axisymmetric, we can always use the corresponding equation or the constitutive relationship, and delta epsilon 1, delta epsilon 3, 1 upon E 1 minus 2 mu minus mu 1 minus mu, delta sigma 1, delta sigma 3. So, this is the equation which we will be using. You can see that this matrix is asymmetric. Now, change in strain due to load from circular tank can be determined if we know the stresses and the elastic parameters. Now, what is given? Vertical and lateral stresses at the middle of the soil layer, this is given already. So, once we know this, we can always calculate what is the strain. Now, settlement is mostly governed by the vertical strain delta epsilon 1. So, once we substitute this, delta epsilon 1 is obtained. Using delta epsilon 1, we can calculate the settlement. How? By integrating for the entire height. So, settlement can be determined by integrating the strain delta epsilon 1 for the height of the soil layer H. Okay, so, that is what we have to do. Once you get this problem for assignment, then you will understand it better. Now, we will discuss a bit on invariance for plane strain and axisymmetric condition. What are invariance? Invariance we have already discussed, which is not affected by the coordinate axis. So, those invariance in terms of plane strain and axisymmetric condition we will see. Okay, so, we have already discussed what is the general expression for deviatoric stress, which is Q, and we have also known that this particular deviatoric stress basically comes from the definition of von Mises failure criterion. So, here Q is equal to 1 by root 2, this is a general expression, sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square. Now, what is the implication once you consider it to be plane strain and axisymmetric, because we know the conditions. So, we just need to apply that into this equation and get the corresponding expression. The next invariant is mean stress, P dash is equal to sigma 1 dash plus sigma 2 dash plus sigma 3 dash by 3. Volumetric strain epsilon V is epsilon 1 plus epsilon 2 plus epsilon 3, and deviatoric strain epsilon Q is root 2 by 3 root of these expression. So, I need not repeat it again because this we have already discussed. Now, for plane strain we know epsilon 2 is equal to 0. There are no other shear strains, so we do not have to discuss, we are discussing in terms of principal stresses and strains. So, epsilon 2 is equal to 0, that will give this equation. We need to substitute epsilon 2 is equal to 0. that will give the expression root 2 by 3 epsilon 1 square plus epsilon 3 square plus we need to expand this epsilon 1 square plus epsilon 3 square minus 2 epsilon 3 epsilon 1. And then if you again do this, you will get that these are all 2 epsilon 1 square, 2 epsilon 3 square minus 2. So, 2 comes out. So, root 2 comes out, then it will become 2 by 3 root of epsilon 1 square plus epsilon 3 square minus epsilon 3 epsilon 1. So, we have got the equation for deviatoric strain corresponding to plane strain condition. And here in case of volumetric strain, it will be simple epsilon 1 plus epsilon 3 because epsilon 2 is equal to 0. Now, for axisymmetric condition, we know the conditions are sigma 2 is equal to sigma 3 and epsilon 2 equal to epsilon 3. We just need to substitute this into the previous equations to get P dash is equal to sigma 1 dash plus 2 sigma 3 dash by 3. Please note this expression, this is the mean stress. This is very important and we will be using this quite extensively throughout this course. So, please make a note of this mean stress, and this is specifically valid for triaxial condition where sigma 2 is equal to sigma 3, epsilon 2 equal to epsilon 3. So, P dash we have obtained, Q will also change, Q is equal to 1 by root 2 into this. You will be very familiar with this particular form of deviatoric stress. Now, when you consider triaxial testing, we know that there is a deviatoric stress which causes shear failure, and there we have taken sigma d is equal to sigma 1 minus sigma 3. Where it comes from? It comes from here, from this general expression. When it satisfies the conditions of axisymmetry, then you get sigma d is equal to sigma 1 minus sigma 3, which is popular, and we know this because we have studied triaxial test. So, it comes from this. So, the genesis is Q in this particular form, and epsilon v is equal to epsilon 1 plus 2 epsilon 3, and epsilon q is equal to 2 by 3 epsilon 1 minus epsilon 3. Your mere substitution gives these expressions. We also know bulk modulus K is equal to P dash by epsilon V, and shear modulus G is equal to Q by 3 into epsilon Q. Now, please make a note here. If you consider bulk modulus, it is mean stress upon mean strain or volumetric strain. Volumetric stress upon volumetric strain gives bulk modulus, but in the case of shear modulus G, it is deviatoric strain upon 3 epsilon q. Where is 3 coming from? Again, this will be dealt as a assignment problem, but you may just look at it from where it will come. So, once we know bulk modulus and shear modulus in this expression, we can also write the constitutive relationship in this form, where P dash and Q, this is the mean and this is the deviatoric stress. We already have discussed about the decoupled behavior by which the soil is studied, which means to say the volumetric component and the shear components are separated, or the deformation components are separated. So, here this mean stress deals with the volume, Q deals with the deformation or the shear behavior, and that K 0 0 3G, 3G comes from here because 3 goes here. So, 3G is Q into epsilon Q, epsilon V epsilon Q. So, this is how it is done. The task for you is to understand where this 3 comes from. So, to summarize this particular lecture, axisymmetric 2D idealization is predominant in soil mechanics. This is very important, and we need to understand more problems relevant to axisymmetric condition. Both geometric and loading symmetry is maintained in axisymmetric condition. Constitutive relationship for axisymmetric condition is discussed for linear elastic isotropic material. and the invariants are discussed for plane strain and axisymmetric condition. Okay. So, with this we are almost nearing to the end of module 1, where we have discussed some of the basics of continuum mechanics which may help you to learn further. So, this is all from this lecture. We will see in the next lecture. Thank you.